wake up from not only particle size distribution, but to detect the bioaerosols. And I don't know how many of you heard of the valley fever in the Bay Area, right? And like the wildfire is not only dangerous because of the particulate sizes, but also the content it's carrying over from the wild areas that were never exposed to humans before is now reaching us. And especially like one of the side we were interested in for stage later on is that the pesticides being burned in the field actually creating these dangerous chemicals into the air that we want to make a sensor that can be portable. And so that Jack will be talking about it. And Jack was my very first student here at Cinema State. And he went from even looking for a little tiny screw that is surprisingly hard, because if anybody worked with a screw before, you'll know how many different thread and size and metric and inches and right? That's right. And he persevered and he whole year spent with us. All right, Jack.
My name is Jack Dawson. I worked with Professor Christine Coe. And my project is on analyzing airborne particles in a local environment using DLS, but primarily WIBs. So we'll talk about that here in a second. What I'm going to walk you through here today, we'll talk about air quality and the importance of air quality, the device WIBs itself, the personal setup that we made here in the lab, and then we'll talk about the sample we tested and the results we got from that. So air quality, obviously seemingly becoming more and more important, especially in the last few years. As you can see all the masks in the room, right? So the issue with air quality, Professor Coe talked about it, but there's no real way to test real time locally what is in our air. There are ways to do it in a lab, but a portable setting hasn't really been feasible. So our solution was to model that WIBs device and make it portable. So what is WIBs? WIBs is the wideband integrated bioaerosol sensor. Quite a mouthful, so I'll call it WIBs. This is, like I said, the instrument that's going to be doing real-time measurements for these biofluorescent and a couple other factors that we'll talk about for how it identifies these particles. It's going to be measuring, relative measure of shape. So we'll talk about aspherity factor, how fibrous the particle is versus spherical. We'll talk about the bioluminescence properties, let me rephrase that, the fluorescent properties and the particle size itself. This solves our problem because it's real time. The problem is this is in a lab setting and these are very, very expensive and not super portable. So our device is going to model this device, but making it portable, making it affordable and accessible. So preparing the samples, we got this action shot here. Best part about the project was going out and picking flowers. So we chose pollen as our sample. So we picked these flowers, brought them into the lab, cut out the pollen from them to make a solution that we could aerosolize. Because obviously we need it aerosolized so we can tell the model what's going to be in the air. So we take these samples, we then put them through what's called a vortex genie, which is going to vibrate the pollen into our sample, giving us a solution of the two. Then putting it into this device called an atomizer. So we're going to have an intake valve putting air in. We'll have our sample on the inside, which is then going to have the pressure pushing it through to the outtake towards where we're going to be testing it. More on the setup. So we talked about a little bit about the code. Angel used his Raspberry Pi. Mine was a little bit different. I used the computer in the lab. A little bit of a love-hate relationship with me and that computer. It's kind of horrid, but we used Python as well, looking at initially intensity over time and more primarily the, through the spectrometer, the wavelength over time. So that code was pretty easy to write, pretty straightforward. The atomizer we talked about, that was what's going to be flowing into this side right here. The air is going to be passing through. let's see here. Yeah, so we have the spectrometer with the fiber optic coming down. That's going to be orthogonal to our laser coming in, which is going to be running pretty much like this, straight through it. It's then having this black box, which was going to be the what's making it portable, having it inside the black box, but also makes a really nice background so we don't get any interference with our light. The spectrometer is going to be coming into that fiber optic. That's going to be giving us our wavelengths and our spectrums. And then we also need this filter, which is very important. This picture doesn't show it, but it's in between the fiber optic and the glass tube itself. This is going to make sure we're not getting any wavelengths early or smaller than 400 nanometers, because ideally we want to be looking past that, especially for fluorescence. So now modeling that device, right? So we saw the WIBs. How do we make it happen? Portably, smaller, cheaper. Well, we use this spectrometer to measure exactly what a WIBs would measure. We look at particle size, right? A spherity factor. So again, how spherical, how fibrous it is. And then fluorescence intensity in 3 different fluorescent channels. So what ours did differently was measuring just in 1 fluorescent channel. But that's kind of really all you need to identify the particle, which is nice. And then through that, we can infer, biological material in particles. We can tell what these particles are in real time. So before we take any data in, we have to do what's called a background, or take a background data point. So this just means we're going to run the exact setup with nothing going through the glass tube in the setup. This is super important because you're going to have a lot of interference. Maybe there's a light leak somewhere. Maybe there's some fluorescence coming from something else. So just being able to take this background lets us, which I'll touch on in a little bit, clean up our data, make it a little less noisy. So this was our first data point with the pollen. Took a little bit to get. And I didn't explain the graph super well in the last image, but we're looking at wavelength in our x-axis and intensity in our y-axis. Apologize for the images being poor quality. Like I said, me and that computer don't really get along. So these are just pictures from the screen. Our pollen sample was rose pollen. And like I said, noisy data. So you can see we have this nice peak here between about 500 and maybe 560 nanometers. But it's very noisy. You can see it's a clear peak, but it's still pretty noisy. However, what I want to really point out right here is at about 420 nanometers, there's that slight peak. But as a scientist, you can't really say that's a firm peak. You really can't say that that is real data because it's very, very noisy. There's a lot of, spikes around it. It could just be a glitch. You don't really know. So where that background comes in is what we do a background subtraction, or we're going to take this data, subtract the background from it to get rid of all of that background noise and hopefully get some really clear data. So through that process, we get our final product, which looks so much better. You see that clear peak at 420 nanometers. We have this really, really nice peak here from about 500 to 560 nanometers. So those are kind of the clear points, the key points, or these clear real spikes in our data. And for each exposure, we're doing about 3 seconds, for those of you who are curious. The results of this, it's exactly what we wanted. So just going back to the last slide, 515 to 420, 500 to 560. That's what we got from our pollen. It turns out the peak fluorescence of pollen samples are exactly that range. It couldn't have been more on the money. So through that, we proved that it works, which is really, really exciting. We are able to identify the particles, we're able to do it in real time, and we can make it portable. So really, really, really cool to see that. What's next? So like we talked about, making it portable, getting it on the cart, that black box, which I showed you an image of, having the laser in it, having the fiber optic in it, testing it in the field. That'll go on to phase 2, which hopefully will be continued next year. Thanks, everybody.
implementation labor?
I believe it was. Oh shoot! Did I not put that on there? I actually don't remember off the top of my head. Professor Coe, do you remember? 360. Thank you. Sorry about that.
I actually have a quick one.
Yeah.
So when you chose that range off of, looking at your plot, were you just sort of eyeballing it, or?
Oh,
was it
for when
like-
we kind of got it a little bit. So from
Yeah,
here
'cause
to
the
here.
fact that the range was exactly what you expect. I mean, were you just like looking at it and you're like, oh, that peak looks like it's around there?
100%.
Okay.
100%. So yeah, because obviously this is going up to about 2,000 as far as intensity. So the peak's only going to like less than 1,000. So being able to bring that range down and kind of make it look a little bit nicer.
But yeah, so I'm saying like the fact that you picked the lower end to be 415, was that like just by
Oh, that's because of
glancing
the,
at it, or did you?
Yeah, so that's where our long pass filter comes in, kind of blocking before 400 more or less. But yeah, we knew that pollen was supposed to be in these ranges, so that's kind of what we were targeting with where we were looking. If that makes sense.
You should account for like digital noise from the sensor.
Digital noise from the sensor. Well, that's actually a really good point. So you see we do have a few little lines here, here, and here, right? So like those kind of just like random vertical lines. So that's pretty much what those could be. They're kind of just glitches that could come from that, from the horrendous lab computer, but definitely could be from that.
Any final questions? All right, let's thank Jeff.
Okay, so we've reached our